Hey everyone, and welcome to the Conrad Chemistry Thanksgiving Review Slides. You're in the right place because today we're going over what you've learned this entire semester. Follow along in your copy of the Google Slides. For every lesson that we're going to review, there will be a few ACP sample questions. Try your best, do that on your own, and we'll go over those answers when you come back. Now, you don't have to complete this in one sitting. You can pause the video whenever you need to either work on the slides, or you can take a break and save it for another time during your Thanksgiving break. But the biggest question to ask yourself is, when you're done, are you ready to take the ACP? How to complete the slides? Well, the main thing you need to do is just to keep watching this video and follow along, filling out your guided notes. And like I said, at the end of each lesson, you're going to answer a few sample questions. Now, some of the tools you're going to need are the same tools that you've used throughout the semester. You always need a periodic table that's been attached to the Google assignment. At home, you want to use a scrap paper and pencil in order to set up your problems where it's required, and need to use your Desmos calculator when it's time to do math. The first thing that we learned this year was modern atomic theory. We learned about 5 scientists, we learned about their ideas of the atom, and we learned that their ideas led them to design different atomic models. And the thing that we also learned is that the way that we think the atom has changed over time. So let's go ahead and talk about the 5 scientists that we learned. So the first person that we learned about was John Dalton, and that was in the year 1803. And the main idea that John Dalton had was, John Dalton said that the atom is the smallest particle, right? He said that the atom is the smallest particle and that it cannot be divided, right? It cannot be divided. And so we call his design model the bowling ball, okay? His was the bowling ball design. J.J. Thomson comes along in 1897, and J.J. Thomson discovered the electron, okay? And he discovered that it was negative. So J.J. Thomson realized that John Dalton was partially correct. But J.J. Thomson had to include the electron in his model, which we call the plum pudding model, right? The plum pudding or the cookie model. So J.J. Thomson's biggest contribution to atomic theory was that he discovered the negative electron. Now we're going to go to Ernest Rutherford in the year 1913. And through his gold foil experiment that we're about to cover, he discovered the nucleus. And he also said that the atom is mostly empty space. And so because he discovered the nucleus, we call his model the nuclear model, okay? Pretty simple. Now we go to Niels Bohr, and we're going to say that his year was 1917. And Niels Bohr said that electrons surround the nucleus in specific energy levels. I think you guys are pretty good with remembering this one. Okay? And we call his model the planetary model. Because if you remember, the electrons surrounding the nucleus in specific energy levels kind of looks like the different planets revolving around the sun. Now we go to Werner Heisenberg in 1926. And Werner Heisenberg discovered the uncertainty principle. We got to talk about this. What is the uncertainty principle? Well, he said that it is impossible to know the location of an electron. It is impossible to know the location of an electron. And because of that, that led him to design the cloud model. Let's talk about two major experiments that contributed to modern atomic theory. First of all, we have, let me get my highlighter out. We have J.J. Thomson, and his experiment was called the cathode ray tube experiment. So, J.J. Thomson, if you look at my highlighter, let's look at this image on the bottom. J.J. Thomson shot a ray of particles in the tubes, and he noticed that these particles were bending towards the negative plate, or towards the positive plate right here. So, J.J. Thomson, like we talked about in the last video, or the last slide, he discovered the electron and that it was a negative particle. Let's go ahead and go to Ernest Rutherford. His experiment was called the gold foil experiment. And let's look at this picture right here that I'm highlighting, right? Okay, Ernest Rutherford, what he did was he shot these alpha particles at a bunch of gold atoms. And he noticed that most of the atoms, most of these particles were passing through the gold atoms. So because of that, he discovered the nucleus and that the atom is mostly empty space. So you need to remember J.J. Thomson and the cathode ray tube experiment. And because of that, we discovered the electron. And you need to remember Ernest Rutherford conducted the gold foil experiment. And because of that, he discovered the nucleus and that the atom was mostly empty space. Okay, so what I would like for you to do in this slide is I want you to drag the atomic models to their correct scientist. And I've laid them out for here. Niels Bohr, looks like his model is not showing up, but his was the planetary model, so it should look something like that, students, okay? So go ahead and drag those to the correct location on your Google Slides. Okay, so here are two ACP sample questions. Go ahead and pause the video and do the best you can to answer these correctly, and we'll go over these when you come back. Good luck. Okay, so we're moving on to atomic structure. So let's go ahead and work on this section on the left, and we're going to go over the different particles and locations of the atom. So let's go ahead and start with this red particle that happens to be positive. Well, that is going to be the proton. And let's worry about this blue particle right here that I just circled. It says a blue particle with a neutral charge. That is going to be the neutron. Try to think neutron, neutral, right? Okay, both of these particles, the proton and the neutron, they are going to be located in the center of the atom, and we call that location the nucleus. Now let's go ahead and pay attention to this particle that I'm just circling right now that you can see. And it's a negative particle that's surrounding the nucleus, and we call this particle an electron. Now what I want us to focus on is I want to focus on this vast area surrounding the nucleus, okay? I just highlighted it pink. This area is known as the cloud, right? Due to Werner Heisenberg. Now what I want us to do is I want us to focus on this table over here, because we need to know the three particles of the atom. We need to know where their location is, and we also need to know their location, mass, and charge. So let's deal with the proton. The proton is located inside the nucleus. It has a mass of 1, and it has a charge of 1 plus. The neutron is also located in the nucleus. It also has a mass of 1, but we need to remember that it has no charge at all, so it's 0. Finally, with the electron, it is located in the electron cloud. The electron has no mass, but it has a charge of 1 minus. Now let's go ahead and pay attention to what is atomic mass. Well, the only particles that have a mass are the protons and the neutrons. So in order to calculate the atomic mass, we need to add, I got the wrong pen. We need to add the protons plus the neutrons. That is going to calculate our atomic mass. Let's go ahead and go to the next slide. We need to understand ion formation. First, let's talk about what a neutral atom is. So go ahead and put neutral here at the top. And a neutral atom is an atom that has no charge due to having the same number of protons and neutrons. This is what a normal atom is. And let's go ahead and look at this section that I'm highlighting. This is a neutral atom. First of all, we're dealing with fluorine because we have 9 protons. And atomic number 9 is fluorine. It's a neutral atom because let's take a look at these electrons that I just circled. We have 9 protons and we have 9 electrons. So the protons are going to give us a 9 plus charge, but the negative electrons are going to give, the 9 electrons are going to give me a 9 minus charge. These charges cancel each other out, and it is a neutral atom. That's what I meant when we were going over this first definition or first type of atom. Now what we want to do is we want to focus on, let's go ahead and define what is an ion. Okay, so I'm filling that right now. And it says an ion is an atom with a positive or negative charge due to losing or gaining electrons. When electrons change, we form an ion. Let's go ahead and take a look at the same atom. We still have fluorine because we have 9 protons, but pay close attention to the number of electrons. We gained an electron. And if we lose or gain electrons, we become an ion. Now, because I have 1 more electron, let's take a look at the charges. So I have 9 protons, so that's going to give me a charge of 9 plus, but I have 10 electrons, so now I have a 10 minus. So that is going to have this ion have a negative 1 charge because that's the difference. Now, a very important question to answer here on the bottom is, can an atom lose protons? And for now, we're going to say the answer is no. We're focusing on gaining or losing electrons, and that's what makes you an ion. So what I want to do right now is I just want us to have, let's just go ahead and fill out this table to practice so we understand atoms, ions, or neutral atoms. And it'd probably be a good idea to have your periodic table out because we're dealing with elements and atomic numbers and such and such. So let's go ahead and talk about potassium. Well, potassium is atomic number 19. That means that it has 19 protons. Now let's look at the protons and the electrons. We have 1 more proton than electron, so we're going to have a 1 plus charge. And because it has a charge, this is an ion. Let's go ahead and go to carbon. We know that carbon is atomic number 12, so that means it has 12 protons. And actually, carbon is not atomic number 12 Carbon is atomic number 6, so that means it has 6 protons. Now let's take a look at, we said we had 6 protons, and we also have 6 electrons. So that means from the protons, we're going to have a 6 plus, and from the electrons, we're going to have the 6 minus. Whenever we have the same number of protons and electrons, we have a 0 charge, and it is just a regular atom, okay? Now let's go ahead and look at bromine. Bromine is atomic number 35. We know that we have 35 protons, and that's going to give us a 35 plus charge, but we have 36 electrons, so we have 36 negative. I have one more electron than proton, so I'm going to have a 1 minus charge. This is an ion. We need to cover this type of question because it's a question that many of us are struggling with. So what I want you to do is I want you to read this question. I want you to pause the video, and I want you to decide if you think the correct answer is A, B, C, or D. So go ahead and pause this video, and then we'll go over it. Okay, let's go ahead and read this question. I'm going to highlight it. An element in its ground state or neutral atom has its subatomic particles listed below. So here we have an atom, and it has 51 protons, 59 neutrons, and 51 electrons. We are dealing with a neutral atom because we have the same number of protons and electrons, 51 and 51. So the positive and negative are going to cancel out, leaving us with a charge of 0. But we need to pay attention to the question. And the question tells us down over here, which table shows the quantity of subatomic particles for this element when it forms a negative 3 charge. So we need to go from a neutral atom at the top to an atom that has a negative 3 charge. So we need to ask ourselves, what type of situation would exist in order for us to have a 3 minus charge? Well, first we have to understand that we cannot gain or lose protons. So any one of these questions that changes the number of protons at 51 is not a right answer. The only thing that the atom can lose or gain are electrons. So option A is incorrect because it's changing the number of protons. If we change the number of protons, we have changed the element, and we don't want to change the element. We just want to form an ion. So let's take a look at option B. Right over here, let's look at B. Our protons are the same, which is good, but our electrons are the same as well. So we still have a neutral atom. Look at the neutrons. The question tried to trick you at 56 neutrons. That's not going to help us. So answer B is incorrect. Let's go ahead and look at choice C. We have 51 protons. We want the same number of protons. And now we've changed electrons, okay, which is good. And we've actually lost 3 electrons. So we now have more protons than electrons. If I have more protons than electrons, I'm going to be a positive atom. And we want to get to that negative 3 charge. So option C is incorrect. Let's take a look at the final choice, which is D. 51 protons and 54 electrons. In this situation, I have 3 more electrons than protons. That is going to give me the negative 3 charge. So answer D is correct. Now you're going to have 2 sample questions from the ACP. Go ahead and pause this video and try to answer these questions correctly. And when you get back, we'll go over it. The next unit that we learned about was periodic table families and properties. What I'd like for us to do right now is we are being shown 5 families on the left. A, B, C, D, and E. For every letter over here on the right-hand side, let's go ahead and write the name of the family. So family A is known as the alkali metals. Okay. Family B is known as the alkaline earth metals. They sound the same, but one is alkali and one is alkaline. So we got to know those differences. And by the way, alkali metals are in group 1, alkaline metals are in group 2. Now, let's talk about this big group over here that I'm highlighting right now, C. This family is known as the transition metals. Transition metals. D, group 17, they're going to be known as the halogens. They're the salt makers. And finally, group 18, E, these are the noble gases, sometimes referred to as the inert gases, but we're going to call them the noble gases for right now. Now, one of the most important questions and things that you need to know is how many valence electrons does an element have? Or in this situation, how many valence electrons does a group have? And this chart tells you. Group number tells you. So let's go ahead and look at the group number 1 that I just highlighted. All the elements in group number 1 have 1 valence electron, and so forth and so forth. Now let me tell you a common mistake that students make. Let's look over here on the right-hand side of the table. Now, what a lot of students make the mistake is if you look at your periodic table, you'll notice that you have groups 13, 14, 15, 16, 17, and 18. And a lot of students will look at the noble gas, what I'm circling right now, and they'll say, Mister, the noble gases all have 18 valence electrons. Well, that's not right. What you need to do is you need to look at this 1 and you need to delete it to where, or put your finger over the 1, and then you'll know how many valence electrons elements have on the right-hand side. Don't let it fool you. Look at this chart. So what we need to do right now is we need to fill out this table, and you probably want to use a periodic table because we're going to need it because we're dealing with the family. So group number 1, the alkali metals, they're in group 1. Let's talk about the elements in that family. We have lithium, we have sodium, we have potassium, we have rubidium, we have cesium, and we have francium, right? They all have 1 valence electron. Some of their properties, they are, can I get smaller than that? Let's see, they are extremely reactive in water. I'm just going to put H2O. They are the most reactive elements, right? And they have 1 valence electron. Alkaline earth metals, group number 2. Some of the members in the family are beryllium, magnesium, calcium, strontium, barium. What do you do with dead chemists? You bury them. And finally, we have radium. They all have 2 valence electrons, and some of them, they're reactive, but less reactive than group 1. Okay. Okay, let's go to the transition metals. They are actually groups 3 through 12, and there's a lot of transition metals, so I just gave you about 5 examples. You don't need to put all of them. You can write those down, or you can choose 4 from whatever group you want. And with valence electrons, we're not going to worry about the valence electrons of the transition metals because it gets a little complicated, and not necessarily every element in the same group shares the same number of valence electrons for a complicated reason that we're not going to get into right now. Now let's talk about some of the properties of the transition metals. The transition metals are good conductors of heat and electricity. And they're also malleable. What does malleable mean? It means that you can hammer it into sheets, and they're ductile. It means that you can stretch them out into wire. On to the halogens. They are group 17. Some of the members of the halogens are fluorine, chlorine, bromine, iodine with an I, astatine, and we're going to leave it at astatine. They all have 7 valence electrons, and they like to form salts, right? They all have 7 valence electrons, and they like to form compounds with metals. They like to form compounds with metals. Okay, let's go to the noble gases. They are in group 18. Some of the members of the noble gases, we have helium, neon, argon, krypton, xenon, and radon. Now, they all have 8 valence electrons. Now let's talk about some of the properties of the noble gases. Because they have 8 valence electrons, we know that they have a full outer valence shell. Because they have a full outer valence shell, they do not react with other elements, and they are very stable. They're the most stable elements in the periodic table, and all of it has to do with the fact that they have 8 valence electrons. 8 is great when you're an element as far as valence electrons go. Now, I want to do this question together so that we make sure that we fully understand it. Go ahead and pause this video and see if you can get the right answer. But we're going to go over this during this video. Okay, you're looking at a portion of the periodic table, and the question asked, which element would most likely share the most properties with selenium, Se? So the first thing I want to do is, let's go ahead and highlight selenium. I just highlighted it in pink. It's atomic number 34. And then we need to ask ourselves, which element would most likely share the most properties with selenium? What we have learned is that elements in the same group, in the same column, I just highlighted it, they share similar properties because they have the same number of valence electrons. So what I'm trying to tell you is, anytime you have an element like selenium, the elements that are in the same column, they're going to be most alike. So let's go ahead and look at these answer choices and see if they fit. Okay, I just highlighted selenium. So our first answer choice is arsenic. It says A. Well, let's locate arsenic on the table. Arsenic is to the left of selenium. Yes, it touches it. It's right by it, but it's not in the same group. So we cannot, arsenic is not the right answer. Let's look at B, phosphorus. Phosphorus is touching selenium, but once again, it is not in the same group. So phosphorus is not the right answer. Okay, let's look at bromine. Bromine is to the right of selenium, not in the same group. You're not the right answer. Finally, oxygen is in the same group as selenium, so that's going to be the right answer. And it says over here to justify your answer below, the reason why is, let's go ahead and delete that. Oxygen is in the same group as selenium. I'm just going to put Se, has the same number of valence electrons. I'm just going to put E negative for electron. Very well. Here you have 2 sample ACP questions. Go ahead and pause the video. Do your best to answer these questions, and we'll go over the answers when you come back from the break. Periodic table trends. Okay, it's actually TEAC 5C, but I don't think that really means anything to you. When we're talking about periodic table trends, we're going to focus on 3 properties of atoms and realize that they increase or decrease. They show a pattern on the periodic table. The first property that we learned about was atomic radius. And atomic radius is the size of an atom. So I want you to look at this table that I just highlighted in pink. Now, this is a table and an image that's showing you the different sizes of atoms on the periodic table. And we can see that a pattern emerges. So let's go ahead and fill out the first information. It says atoms get smaller. So everybody look at what I'm highlighting right here. We're looking at a row on the periodic table. And we learn that atoms get smaller as you go across due to increased nuclear charge. Okay. So as we're going to the right, let's start with lithium. As I'm going from lithium to beryllium to boron to copper to nitrogen and to oxygen to fluorine, those atoms are gaining 1 proton. Remember, lithium has 3 protons, beryllium has 4, boron has 5, carbon 6, nitrogen 7, oxygen 8, and fluorine 9. So as we're gaining protons inside the nucleus, that charge of the nucleus, that nuclear charge, is getting bigger and more positive because we have more protons. And it says right here, the protons and positive charge increase and it pulls electrons closer to the nucleus. So that's one way that we know that atoms get smaller as we go to the right. But notice the arrow over here. The arrow is talking about how the trend increases. So I'm highlighting the pink arrow. So atoms get bigger as we go to the left because they have less protons on the same row. Now let's talk about how atoms increase as we go either across a group or up and down a group. Let's look at group number 1, the alkali metals. You can easily see that as we go down the alkali metals, the size of the atom increases. The reason why atoms get bigger as you go down a group is due to increased energy levels. So every time you go down a group, you gain a ring around the nucleus. So obviously, the outer electrons are going to occupy levels further from the nucleus. Okay, the second type of property is called ionization energy. Okay, it's not. Ionization energy. Let's go ahead and write that down. And what is ionization energy? Well, ionization energy is the energy required to remove a valence electron away from an atom. Let's go ahead and look at this periodic table right here. And we can see from the arrows that ionization energy increases as we go from left to right. And it also increases in a group from top to bottom. That's what I'm highlighting right now. You don't have to highlight it, but I'm demonstrating it to you. Let's take a look at 2 atoms. Okay, on the left-hand side, we have iodine and we have fluorine. Now, which one of these atoms has a higher ionization energy? Do you think it'd be iodine or you think it'd be fluorine? Well, let's go ahead and answer the bottom segment. We will say that larger atoms, okay, such as iodine, larger atoms have low ionization energy because their valence electrons are farther from the nucleus. So if you look at iodine over here, let's take a look at, I'm going to circle one of its valence electrons. It's way out there and its nucleus is in the center. This valence electron is so far away from the nucleus that it's not as strongly attracted to it, so it's going to take less energy to remove it. On the other hand, if we look at fluorine's valence electron, it's so close to its positive nucleus that it's going to require more energy to pull this valence electron away from the atom. And that's why larger atoms have lower ionization. I should have put lower right there, but that's okay. So the third property of an atom, which is extremely important, is known as electronegativity. Electronegativity. We've talked about this before, highlighting it right here, and I'm going to abbreviate it as EN. Electronegativity is the ability to attract electrons in bonds. Now let's take a look at this table here. It's a periodic table, but it's actually known as the Pauling scale. And we took a look at this when we talked about bonding and we talked about electronegativity a little bit more in depth. The Pauling scale is a table that assigns a number to every element. You can see hydrogen has 2.1, rubidium 0.8, iron is 1.8, carbon is 2.5. Every atom is assigned, or every element is assigned a number according to the Pauling scale. And the higher the number, the more electronegative you are, which means that you have a greater ability to attract or pull electrons towards you when you're forming bonds. So electronegativity is related to atomic radius. Let's look how it trends. So electronegativity increases as we go to the right, and it increases from top to bottom. Smaller atoms have higher electronegativities, and the smaller atoms are in the top right-hand section of the periodic table. Now, fluorine, everybody highlight fluorine, that has the highest electronegativity at 4.0. And then let's go all the way down here to francium. It has a 0.7 rating. It's the least electronegative element. So here we have two sample questions, or here's sample question number 1. Go ahead and pause it and answer the question. And then I'm going to flip to the second sample question when we're dealing with periodic trends. So go ahead and pause this and do your best as well. Okay, so we're going to move on to average atomic mass. But in order to understand average atomic mass, we need to talk about an isotope. So go ahead and let's fill out that word, isotope. Well, what is an isotope? An isotope is atoms of the same element with a different number of neutrons. I want us to pay attention to the image that's been attached on this slide. We're looking at potassium, but we're looking at 3 different types of potassium: potassium 39, potassium 40, and potassium 41. We can see that each of these potassium atoms has 19 protons. They all have the same number of protons because you have to remember that the number of protons is what makes the element unique. 19 protons is potassium on the periodic table. The minute we go to 18 protons or 20 protons, we're no longer potassium. But let's pay attention to the number of neutrons, guys. This potassium atom has 20 neutrons, the other one has 21, and the last one has 22. So that's what an isotope is. We can have atoms of the same element, but they have a different number of neutrons. Now let's go ahead on the right-hand side and let's talk about percent abundance, okay? What is percent abundance? Well, percent abundance is going to tell us how often each element's isotopes appears. And they're always going to give this to us in a percentage. Let's say 90%. But when we're doing average atomic mass, we want to convert our percentages to a decimal. So how do we do that? We're going to divide the number by 100. And when we do that, we're going to get the decimal that we need in order to solve these problems. Let's go ahead and go to the bottom and let's write the formula for average atomic mass. The formula for average atomic mass is going to be M1 times P1 plus M2 times P2 plus M3 times P3, and on and on and on, depending on how many isotopes that the question has. Now, What do M and what do P mean? Well, M is going to stand for the mass of the isotope, and P is going to stand for the percent abundance of that element. But remember, we have to divide that by 100 and convert it to a decimal. Let's go ahead and go over an example problem. I'm going to go ahead and work this for you in case you're having trouble with this. But it's very important to remember that during the ACP, you need to set this up on paper and then calculate it in Desmos. So feel free to get out a scrap paper because the next problem you're going to do by yourself, and you need to go ahead and do that. Okay, so the question is, what is the average atomic mass of the following element based upon the information that you see? Well, we're dealing with iron because I see Fe, and we have two isotopes of iron. I'm going to highlight them. We have iron 55 and we have iron 56. Remember, what we first need to do is we need to convert our percentages to a decimal. That is the first thing we want to do because we don't want to make the mistake that we didn't convert it. So let me go ahead and let's talk about 14.5. If you go to Desmos and you put it in the calculator, and if you divide 14.5 divided by 100, we're going to get 0.145. Okay? Now, guess what? That's going to be my first percent abundance. Now, let's go ahead and convert 85.5. We're going to divide it by 100 in Desmos, and we're going to get 0.855. Well, that's my second percent abundance. Now I can label for my first isotope, iron 55. The mass is going to be 54.876. That's going to be my M1. And then for my second isotope, my mass is going to be 55.998. So guess what? I've converted my percentages to a decimal and properly labeled them. I found my masses for each isotope. I have my M's, I have my P's. Now we're ready to set this up. So in the calculator, we're going to do what is M1, and I said M1 was 54.876, and I'm going to multiply that by my P1, which is 0.145. I'm going to add plus, and then M2 55.998 times 0.855. That's what I'm going to put in the Desmos calculator, and when I get that, I already pre-calculated it, we're going to get 55.835. I'm just going to round it off. And the units are going to be atomic mass units. But the most important thing is that number. So that's how we do average atomic mass. Go ahead and do the ACP sample question. Good luck, and we'll go over this when we get back. Emission spectrum. This has to do with energy, wavelength, frequency, colors, electrons, and elements. The first thing that we want to remember is the relationship between wavelength and energy. You have learned that, and let's fill this out, the shorter the wavelength, the higher the energy. That's the greatest relationship that you need to understand when it comes to the colors of the rainbow, when it comes to radiation in the electromagnetic spectrum, and even the emission spectrum. Let's go ahead and take a look at the colors of the rainbow. I'm highlighting it in pink right here so you know what we're talking about. You are looking at red, orange, yellow, green, blue, indigo, and violet. Every color has a certain wavelength. And you can see for yourself, you can look at the waves that are being drawn, but you need to understand that a wavelength has an actual measurement. So let's take a look at red. Yes, we can see the wavelength, but we also can see that. And by the way, these measurements are in nanometers, very small lengths of distance, right? Red has a wavelength of 625. Orange has a wavelength of 590, and on and on and on, students. So we can see that. Go ahead and delete that. Remember that the shorter the wavelength, the higher the energy. So we need to pay attention to these numbers. And we need to understand that the lower the number, the greater the energy. So red, if you look at the spectrum, red has the biggest wavelength, so it has the lowest energy. Violet has the smallest wavelength numerically, so it has the higher energy. And one way that we can remember the colors of the rainbow in order from lowest energy to highest energy is an acronym known as Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. And red has the lowest energy. I'm just going to put E down, and violet has the highest energy. The second thing that I want you guys to pay attention to is, I'm highlighting it right now, it's on the bottom. It's the electromagnetic spectrum. These are the 7 radiations of the universe that we put on a graph in order of lowest energy to highest energy. And if you take a look at the waves, right, you can see that the longest wavelengths are on the left-hand side. And radio waves, okay, I'm going to highlight it. Radio waves have the lowest energy because it has the longest wavelength. And all the way on the right-hand side, gamma rays have the highest energy because it has the shortest wavelength. Now pay attention to the right-hand side. I'm highlighting the emission spectrum of an element. All we're doing is, when we're working with an emission spectrum of an element, we're putting together everything that we've learned about wavelength, energy, and color. And so when you're looking at an emission spectrum, pay attention to the colors and pay attention to the numbers. Those colors and those numbers represent a wavelength. And you know that the smaller the number, the higher the energy of that photon that was released by the atom or the electron when it returned back to ground state. Here is one ACP sample question that we would like you to answer about wavelength and energy. Go ahead and pause that and answer the question. And there's another ACP sample question about the emission spectrum of boron. So go ahead and try to answer that, and good luck. After this question, we're going to go ahead and end part 1 of the Thanksgiving review, and we will continue on the next YouTube video.